Welcome students. Last time you have learned the one-top equation or one-top isotherm, and it is the equation which gives the maximum amount of work obtained in isothermal reversible process. And all of you know, in case of spontaneous processes, the free energy decreases, and we have derived last time the equation minus delta G, it is equal to 2.303 RT into log Kp, where Kp it is the equilibrium constant. And again we equate minus delta G for the W max, that is maximum work obtained in a reversible process, and it is given by 2.303 RT into log Kp plus delta N RT. On this basis, the equations for maximum work in case of the following reactions can be derived. Here, the first example we have 2H2 plus O2. It is in equilibrium with 2H2O. Here, the number of moles of product are 2, while the number of moles of reactant are 3. Therefore, the value of delta N here it is equal to minus 1. In the first example, 2 moles of H2 and 1 mole of O2 are considered as reactants, and 2 moles of H2O are considered as products. Therefore, we can write the equation of Wm, that is maximum work, it is equal to 2.303 RT into log Kp minus RT. Since we have minus 1, it is the value of delta N, and we can write the Kp as the P square of H2O divided by P square of H2 into pressure of O2. P raised to 2 because we have taken 2 moles of H2. Okay, and 2 moles we get H2O as a product. Similarly, in the second example, suppose we have N2 plus 3H2, it gives 2NH3. Here there are 2 moles of NH3, that means N2 it is equal to 2, and N1 means the moles of reactant 3 plus 1, that is 4, and 2 minus 4 it is equal to minus 2. Therefore, delta N value here it is minus 2, and we have the equation Wm it is equal to 2.303 RT into log Kp minus 2 RT, where Kp it is equal to P raised to 2 of NH3 divided by pressure of N2 into pressure of H2 raised to 3, and we have delta N value as a minus 2. Similarly, prepare the another examples so that you can understood well the one-top isotherm equation. Then in your textbook, the one-top isopower or the one-top equation, it is given in the following way. Here, the one-top equation represents the temperature dependence of equilibrium constant. The temperature dependence of equilibrium constant. The equation can be obtained by combining one-top isotherm with Gibbs-Helmholtz equation. I repeat, here the one-top isopower, that is the one-top equation, it represents the temperature dependence of equilibrium constant, and this equation can be obtained by combining one-top isotherm with Gibbs-Helmholtz equation. Here we have the one-top isotherm as delta G0 it is equal to minus RT ln Kp, and differentiating this equation with respect to T at constant pressure, we get d of delta G by dt at constant P, it is equal to minus R ln Kp minus RT in a bracket d ln Kp by dt. We used the differentiation of this equation, and we have, this is the differentiated equation, d of delta G by dt at constant P, it is equal to minus R ln Kp minus RT d ln Kp by dt at constant P. Okay, where Kp, it is the equilibrium constant. Then multiplying above equation by T, we get d of T into d of delta G by dt at constant P, it is equal to minus RT ln Kp minus RT square d ln Kp by dt. And here this minus RT ln Kp, it is the delta G0 from equation number this. Therefore, we have this T into d of delta G 0 by dt at constant P, it is equal to delta G0 minus RT square into d ln Kp by dt. Then see. Then now from the Gibbs-Helmholtz equation, we have here delta G0, it is equal to delta H0 plus T into d of delta G0 by dt. This equation we have written in a standard state. This is 0 above G, this 0 above H, and 0 above G. It indicates the standard state here, where delta H0 is the enthalpy change of a reaction carried out in a standard state. And from this equation, we can write T into d of delta G by dt at constant P, it is equal to delta G0 minus delta H0. And comparing the equation 2.88 and 2.90, we get RT square in a bracket d ln Kp by dt at constant pressure, it is equal to delta H0. And here delta H0 under standard condition is not much different than the delta H value at other pressure condition. Therefore, we equate delta H0 with the delta H. Therefore, we can write RT square in bracket d ln Kp by dt at constant pressure, it is equal to delta H. And rearranging this equation, we can write d ln Kp by dt, it is equal to delta H upon RT square. And this equation is the one-Top's reaction Isopower equation. Okay. This equation is known as the one-top reaction isopower or one-top isopower equation. Then rearranging this equation, we can write d ln Kp, it is equal to delta H upon RT square into dt. If delta H is independent of temperature and remains constant, and integrating this equation within the proper limit, we get here integration of dln kp within lower limit kp1, upper limit kp2. This kp1 at temperature T1 and kp2 at temperature T2, and we assume that delta H, it remains constant over the range of temperature. Okay, so here integrating this equation within proper limit, we have written this equation, and the integration of dln kp within the limit kp1 kp2, we get ln kp upper limit kp2 lower limit kp1, and it is nothing but ln Kp2 minus ln Kp1 or ln Kp2 by ln Kp1, and it is equal to, this is the constant delta H by R, and the negative sign here, the integration of 1 by t square, it is minus 1 by t. Therefore, we have taken here minus sign. The lower limit here it is t1, upper limit here it is t2. Therefore, we get here ln kp2 minus ln kp1, it is equal to minus delta h upon r in a bracket 1 upon t2 minus 1 upon t1. Okay, so here, therefore, we can write ln kp2 by kp1, it is equal to minus delta h upon r in bracket 1 upon t2 minus 1 upon t1. And changing this natural log to the log base 10, here we can write this equation as 2.303 log to the base 10 kp2 by kp1, it is equal to minus delta h upon r in a bracket 1 upon t2 minus 1 upon t1. And again we can write the log to the base 10 kp2 by kp1, it is equal to delta h upon 2.303 r into, here we have removed this negative sign and we have taken 1 by t1 minus 1 by t2. Again we rearrange this equation as, here log to the base 10 kp2 by kp1, it is equal to delta h upon 2.303 into r in bracket t2 minus t1 upon t1 into t2. This factor 1 by t1 minus 1 by t2, it is equal to t2 minus t1 upon t1 into t2, where kp1 and kp2 are equilibrium constants at temperature T1 and T2 respectively, and this equation is the integrated form of want of isopower, which is useful to determine the equilibrium constant at any other temperature. If it is at any one temperature is given, provided that delta H is known. That means from these five quantities, Kp1, Kp2, this is third, and T1, T2. Among these five values, if four values are known, we can calculate any fifth value amongst this. This is the application of the want of isopower equation. Then, as per your syllabus, the next point here it is fugacity and activity concept. Fugacity and activity concept. Here, at first, I will explain you here. The concept of fugacity was introduced by the scientist Gilbert Newton Lewis in 1901. The concept of fugacity was introduced by the scientist G.N. Lewis, and fugacity is widely used in solution thermodynamics to represent the behavior of real gases. Then the fugacity is a derived word. This word fugacity is a derived from the Latin word fleetness. From the Latin word fleetness, or the escaping tendency. The fugacity is derived from the Latin word fleetness, or it is the escaping tendency. And fugacity has used extensively in the study of phase and chemical reaction equilibria involving gases at high pressure. In short, the meaning of fugacity here it is escaping tendency. Then the concept of fugacity. Here, for infinitesimally reversible change occurring in a system under isothermal condition. And I mean you are very well familiar with this equation. This dg it is equal to minus s dt plus vdp. Okay, dg it is equal to minus s dt plus vdp. And for infinitesimal reversible change occurring in a system under isothermal condition, that means temperature constant, this dt change in temperature becomes 0 and this term becomes 0. Therefore we have dg it is equal to vdp. For 1 mole of an ideal gas, P in the above equation may be replaced by RT by P. You know, for 1 mole of gas, RT it is equal to PV, or PV it is equal to RT. And in case of ideal gases, this is true. But in case of real gases, it is not true. And the scientist Louis, he wants to apply the law of mass action to the real gases, and during his studies he found the similarity in between the real gases and ideal gases at low pressure condition and high temperature condition. And this Phi it is equal to RT by P. It holds good only a limit range of pressure and temperature. And phi it is equal to RT by P. From the ideal gas equation we have P phi it is equal to RT, therefore phi it is equal to RT by P. And substituting the value of phi here as RT by P, we can write this dg it is equal to RT in a bracket dP by P, and it is equal to RT into dln P. Okay, and this equation is applicable only to the ideal gas. And the Lewis he used or he applied this equation to the real gases in uh, okay, then the following equation thus provides the partial definition of fugacity, or the mathematically fugacity it is defined as dg it is equal to RT d ln f, where this R gas constant, T it is a absolute temperature, and F it is a fugacity. And integrating this equation we get G it is equal to RT ln F plus C, where C is the constant that depends on temperature and nature of the gas. Okay, and here the effect of temperature and pressure on fugacity. By integrating equation dg it is equal to RT d ln F between pressure P, that means any pressure P, and standard pressure P0. Here we get G minus G0 it is equal to RT ln F by F0, that is fugacity at any pressure divided by fugacity in a standard pressure condition. Okay, so time being, remember that G minus G0 that is equal to RT ln F by F0. And here the as the scientist Louis he introduced the concept of fugacity, and the fugacity it is the escaping tendency. Suppose consider a water taken in a beaker which is kept at a constant temperature pressure condition. Then what happens? It is a natural tendency of water molecules to escape from liquid state and enter into the vapor state. and at the same time the vapor state water molecules they escapes into vapor state and returns back to the liquid state. That means you are very well familiar with the phenomenon of evaporation and condensation, and this escaping tendency of any substance, it is termed as fugacity. So we will see the description of fugacity which is given in your book. So see here the concept of fugacity and activity. Here the fugacity, the change in free energy for real expansion of a gas, it is given by this equation delta G integration of nRT into dP by P and within pressure limit P1 P2. Here for any gases expansion at pressure P1 lower and higher pressure P2, we can write the change in free energy by this expression, that is integration of nRT into dP by P. This term it is the variation of pressure. Okay. Then the above equation for 1 mole of an ideal gas, we can write delta G it is equal to RT into dP by P. Here the lower limit is P1 and upper limit is P2, and integration of this equation it is equal to RT ln P2 by P1. That means the change in free energy for the expansion of a gas, it is given by RT ln P2 by P1, where this ln is the natural log to the log base E. Now, it is observed that while applying the law of mass action to the highly concentrated solutions or gases at high pressure, the deviations from the ideal behavior are observed. The study is much important in case of electrolytes as ionic solutions deviates considerably even at low concentrations. So, when we apply this equation to the real gases, particularly at high pressure, it was not possible to integrate this equation as phi is not equal to RT by P for real gases. In order to remove this difficulty and to retain the generality, the American scientist the American chemist G.N. Lewis introduced a new function F, which is known as fugacity, which does not depend on the nature of the gas. And here the concept of fugacity it is cleared here. Consider a system consisting of water in contact with its vapor at constant temperature. It has been observed that the water molecules in liquid phase will have a tendency to escape into the vapor phase by the process of evaporation. At the same time, water molecules in a vapor phase have tendency to escape into the liquid phase by condensation process. These two escaping tendencies become equal, the system is said to be in equilibrium, and the idea that each substance in a particular state has a tendency to escape from that state is perfectly general, and this escaping tendency is the fugacity. Okay, the escaping tendency is the fugacity. Here, the derivation of fugacity. The fugacity may be defined mathematically here by this equation. dg it is equal to nRT d ln f. Integrating this equation, we get g it is equal to nRT ln f plus c, where c is the constant of integration when f it is equal to 1, g it is equal to g0, and the above equation becomes, at this condition when f it is equal to 1 and g it is equal to g0, we can write this equation as g0 it is equal to 0 plus c, or constant of integration c it is equal to g0. Then substituting the value of c in this equation, we get g it is equal to g0 plus RT ln f, where g0 is the free energy of n moles of real gas when its fugacity is unity, that is the free energy in a standard state. And integrating this equation 2.99 for 1 mole within limits, proper limits here, we can integrate dg within limit g1 g2 and rt dl and f within limit f1 f2. We get delta g it is equal to rt ln f2 by f1, where 1 and 2 subscripts represent initial state and final state. Here fugacity is expressed in the same units as a pressure. Okay, then if f is the fugacity in any state and f0 is the fugacity in a standard state, then we can write the equation g it is equal to g0 plus rt log f by f0, where f by f0 it is equal to activity. Okay, that means fugacity of any substance in any state divided by the fugacity of said substance in the standard state, and this ratio it is given by activity. Thus activity of a substance may be defined as the ratio of the fugacity of substance in a given state to that in its standard state. Then the standard state of substance may be defined as a state in which the activity is unity. Therefore, the activity can also be defined as the concentration, which is idealized so that the law of mass action will be exactly applicable and will be equal to the product of concentration C and activity coefficient gamma. So, we can have the equation for activity A, it is equal to concentration into activity coefficient, that is C into gamma. This product it gives the activity, or we can write the equation for activity coefficient gamma it is equal to activity divided by concentration. Okay, so remember these mathematical expressions for fugacity and the activity concept and activity coefficient, and for the tomorrow's lecture you will learn the partial molar quantities and particularly the partial molar volume, the concept of chemical potential and Gibbs-Duhem equation. So study well, and if you have doubts then ask me, and probably in the next uh, week you will have to attempt a test on the previous chapter. So thank you for your patient listening.